A comet's tail is supposed to run away from the sun, pushed back by the sunlight and the solar wind like hair in a strong breeze. So when the interstellar visitor 3I Atlas started showing a strange sunward anti-tail, it instantly raised eyebrows. In recent post-perihelion images, the comet's coma looks almost teardrop-shaped, with a faint extension that seems to point toward the sun. And now, a new idea is making the rounds. What if that anti-tail isn't a tail at all, but a swarm of companion objects moving with 3I Atlas? Out past the familiar traffic of planets and asteroids, there's a kind of visitor that almost never shows up. Something that wasn't born here, isn't bound here, and won't stay here. That's what makes 3I Atlas so gripping. It isn't just another comet, it's the third confirmed interstellar object ever seen passing through our solar system, meaning it arrived from beyond the Sun's gravitational family on a path that doesn't loop back. If you trace its trajectory backward, it doesn't lead to a distant Kuiper Belt reservoir or an Oort cloud orbit. It leads outward, into interstellar space. The story begins with a routine scan of the sky, one of many thousands, by a survey designed to catch fast-moving objects before they surprise us. On July 1st, 2025, the Atlas Survey Asteroid Terrestrial Impact Last Alert System, operating from Rio Hurtado, Chile, reported observations to the Minor Planet Center. At the time, it was just another faint smudge in a sea of faint smudges, tagged with a provisional designation and flagged for follow-up. But almost immediately its motion looked wrong in the best possible way. The early orbit solutions didn't fit an ordinary closed solar system path. They hinted at a hyperbola, an open trajectory that screams this object is not staying. To understand why that matters, it helps to picture what homegrown solar system objects do. A typical comet is like a long-term tenant. It might have a stretched-out ellipse, wandering far and then returning, but it's still bound to the sun. An interstellar object is different. It's more like a traveller cutting across your yard and disappearing down the next street, never to be seen again. The difference shows up mathematically as a hyperbolic orbit, not a loop, but a flyby. NASA describes 3I Atlas as interstellar specifically because of that hyperbolic orbital path, the kind that doesn't close back around the sun. Once the alert went out, astronomers did what they always do when something looks bizarre. They widened the net. They pointed more telescopes at it, refined the astrometry, and then, crucially, went hunting through older images. This is called precovery, and it's one of the quiet superpowers of modern astronomy. This sky has been photographed so often by so many surveys that new discoveries sometimes turn out to have been there for weeks, just unnoticed. For 3I Atlas, NASA notes that pre-discovery observations were pulled from multiple Atlas telescopes and Caltech's Zwicky Transient Facility, extending the observational timeline back into June 2025. The longer your observation arc, the better you can pin down the orbit, and the harder it becomes for a weird orbit to be a fluke. With data piling up, the identity of the object crystallized. It wasn't an asteroid masquerading as a comet, it was behaving like a comet, with an active coma and dust output that bright telescopes could tease out. And its designation told the rest of the story. The I in 3I Atlas literally stands for interstellar, a category the International Astronomical Union uses for these rare outsiders. The 3 is almost haunting. It means we can count the entire class on one hand. ESA spells it out plainly. 3I Atlas follows 1I/Oumuamua in 2017 and 2I/Borisov in 2019 as only the third of its kind ever observed. That short list is part of the magic, and part of the frustration. With Oumuamua, we saw puzzling behaviour that sparked endless debate, but we caught it late and watched it briefly. With Borisov, we got a more comet-like interstellar object that behaved in ways astronomers could recognise, but it was still just one example. Now 3i Atlas becomes a third data point, and that's when patterns start to matter. 3 is still tiny, but it's no longer a complete anomaly. It's enough to ask, are interstellar visitors typically more like comets than asteroids? Are our detection methods biased towards seeing active, gassy objects? Are we missing a whole population of silent, dark interstellar rocks that don't announce themselves with glowing comas? What makes 3i Atlas especially watchable is that we didn't just glimpse it and lose it. We tracked it through a meaningful part of its passage. NASA notes it reached its closest point to the Sun around October 30th, 2025, at about 1.4 astronomical units, just inside Mars' orbit, and that it never posed any danger to Earth. Its closest approach to our planet was still distant, roughly 1.8 astronomical units. In other words, close enough for serious study with telescopes, far enough that it's purely a scientific event, not a doomsday headline. Even those distances are a reminder of scale. An astronomical unit is the average Earth-Sun distance, so 1.8 astronomical units is not near in a human sense. It's hundreds of millions of kilometers. Yet for astronomy, it's close enough that spacecraft elsewhere in the solar system can get unusually valuable vantage points. ESA even used the comet as a kind of rehearsal for orbit refinement, improving predictions by combining Earth-based observations with data from a different location in space. The point isn't that we needed to defend ourselves, it's that interstellar visitors move fast, and precise tracking is hard. Every extra viewpoint helps, and fast is the right word. ESA highlights the comet's speed at closest approach to the Sun as roughly 250,000 kilometers per hour, emphasizing how extreme these flybys are. That kind of velocity isn't just a fun fact, it shapes everything about how the comet behaves, how it responds to sunlight, how quickly it changes, and how narrow our window is to observe it before it fades into the outer dark again. So think of 3i Atlas as a moving laboratory sample. It's not merely old, it's potentially ancient in a different way than most objects we study. Every planet, moon, and asteroid in our solar system shares a common origin story. Interstellar comets don't. ESA calls them true outsiders, carrying clues about the formation of worlds far beyond our own system. That's the bigger scientific promise. This object is a messenger that was shaped around another star, perhaps in a disk with different chemistry, different temperature gradients, different impacts and collisions and freeze-thaw cycles. Even if its overall behavior looks familiar, the details, what gases it releases, what dust dominates, how its surface responds to heating, can tell us what other planetary systems make. In a way, the naming itself is part of the narrative. Atlas is not a person, it's a survey. This is modern discovery. Automated telescopes, pipelines, and global follow-up networks. NASA explains it directly. The comet is named for the Atlas survey team, and the designation embeds what it is, interstellar, right into the label. You don't have to be an expert to read the headline and understand the premise. It's like the universe stamped its passport. But while the label is clean, the object itself is messy, in the best cometary way. Even early on, Hubble observations showed a distinctive dust environment, and worldwide teams kept watching as the comet approached the Sun, slipped too close for safe observation, and then re-emerged afterward for its second round of scrutiny. NASA even lays out that rhythm, visible to ground-based telescopes through around September 2025. lost in the sun's glare, and then reappearing by early December 2025, giving astronomers a before and after look at what solar heating did to an interstellar nucleus. That after part matters because comets aren't static. They're not rocks, they're active worlds. The moment a comet gets warm enough, it begins to shed itself. Volatile ices turning to gas, dust grains lifting off, jets forming, the coma blooming like a temporary atmosphere. ESA notes that by late summer 2025, observations were already revealing a variety of volatiles and ice signatures in the coma as the object warmed, consistent with an active comet. Even if you never remember the chemical names, the takeaway is simple. We weren't just seeing a point of light, we were seeing a changing system responding to the sun. That's why this particular visitor feels like a character more than a dot. It arrives from the black between stars, it accelerates through the inner solar system, it flares into activity as sunlight hits unfamiliar ice. It passes inside Mars' orbit, and then it keeps going, headed back out, carrying its secrets away unless we've captured enough data to read them later. And it's worth emphasizing what this is not, because the internet tends to sprint ahead of evidence. Mainstream comet researchers cited by Sky and Telescope have stressed that, despite speculation, 3I Atlas is doing the things comets do, and that unusual-looking features can still have straightforward physical explanations. That doesn't make the story less exciting, it makes it better. The mystery isn't manufactured, it's the real, slow, disciplined process of figuring out what a foreign comet is made of, how it behaves, and what it can teach us about planetary systems that aren't ours. If you've ever seen a classic comet photo, you probably remember the rule. The tail trails behind like a scarf flapping as the comet speeds away from the sun. But that rule is actually a simplified version of something even cooler. Comet tails don't merely trail, they get built by sunlight and then shaped by invisible solar forces. A comet starts out as a small dark nucleus, a lumpy mix of ice, dust, and rocky material. Far from the sun, it's basically inert, like a frozen cinder. But as it falls inward, sunlight begins to warm the surface. The key step isn't melting like an ice cube, it's sublimation. Ice is turning directly into gas. That gas doesn't seep out politely. It blasts out through pores, cracks, and vents, often in jets. The escaping gas drags dust with it, and suddenly the comet grows a temporary atmosphere called the coma, a hazy envelope surrounding the nucleus. From that coma, the tails are born. Now here's the twist. Most comets don't have one tail. They usually have two main tails, and they exist for different reasons. One is the dust tail. Dust grains are electrically neutral little specks. Think smoke particles, sand grains, and everything in between. Released from the nucleus and carried outward by the streaming gas. Once they're free, they become tiny sailing ships in a sea of sunlight. Photons from the sun carry momentum. When sunlight strikes a dust grain, it delivers a gentle but constant push called radiation pressure. It's weak compared to everyday forces, but in space, when you're a microscopic grain with almost no mass and nothing to slow you down, it matters a lot. This is why the dust tail often looks broad and softly curved. Different grain sizes get pushed by different amounts. Small grains get bullied hard by sunlight and peel away more dramatically. Bigger grains resist that push and stick closer to the comet's path. The dust tail also tends to look whitish or yellowish because it's mostly reflecting sunlight, a cosmic headlight beam bouncing off dust rather than glowing from its own energy. The other main tail is the ion tail, often called the plasma tail. This one is less like smoke and more like a neon sign in a wind tunnel. As gas molecules stream out into space, sunlight and the surrounding plasma environment can strip electrons away, turning some of that gas into ions, electrically charged particles. Once the gas becomes charged, it stops behaving like ordinary gas. It gets grabbed by electromagnetic forces and swept into the flow of the solar wind, the constant outpouring of charged particles from the sun that carries the sun's magnetic field outward through the solar system. That's why ion tails are often straighter, thinner, and can show sharp kinks or disruptions. They're tracing magnetic structure and space weather, and crucially, the ion tail tends to point directly away from the sun because it's being sculpted by the solar wind blowing outward. So when people say a comet's tail points away from the sun, what they really mean is the sun is actively pushing the comet's material outward in two different ways. Dust gets pushed by radiation pressure. Ionized gas gets dragged by the solar wind and embedded magnetic fields. And this is where the so-called anti-tail becomes such a delicious brain twister. Because in normal intuition, a tail is like a flag. It flaps behind you. If it points the wrong way, you assume the wind reversed. But with comets, the wind and the geometry are more complicated. An anti-tail is usually not a tail that is truly being blown sunward. It is most often a trick of perspective created by bigger, heavier dust particles that don't get pushed as easily. Those large grains tend to remain closer to the comet's orbital plane and can form a faint, thin dust sheet or trail along the comet's path. Most of the time, that sheet is too diffuse to notice, but if Earth's viewpoint lines up just right, especially when we're looking nearly edge-on through the comet's orbital plane, that dust sheet can suddenly look like a narrow spike projecting from the coma in a direction that appears to point toward the sun. It's like seeing a misty road from above versus seeing it from the side. Same structure, totally different visual impact. This is why astronomers often describe classic anti-tails as real, but also an illusion. The dust is real. The spike is real. The interpretation that it's being blown sunward is what's misleading. You're not watching a tail defy the sun. You're watching older dust sitting in the comet's orbital plane suddenly become visible, because the viewing angle makes it stack up in your line of sight. And the dust-size story matters even more than people think. Imagine two grains released at the same moment. One is tiny like flour, one is chunky like sand. Sunlight can shove the flour grain noticeably, curving it away and spreading it out. The sand grain barely budges, so it keeps drifting roughly where it should be if it were just following the comet's path. Over time, those big grains become a kind of breadcrumb trail. The comet's past path written in particles. And a breadcrumb trail, viewed from the right angle, can masquerade as a tail pointing somewhere surprising. That's the standard physics background. Two tails, two forces, and a third apparent feature that's mostly geometry plus particle size, which is exactly why anti-tails are such a useful diagnostic. They force astronomers to ask, what sizes of grains are present? When were they emitted? And how is the dust distributed in 3D? An anti-tail tends to imply a population of relatively large grains, and a viewing geometry that makes the orbital plane dust sheet show up clearly. Now, keep the whole picture in mind. The nucleus is shedding gas and dust. The coma is a staging area. Dust is getting pushed by radiation pressure and curving. Ions are getting yanked outward by the solar wind and magnetic fields. And the anti-tail is often a slice of the comet's dust history seen edge-on. With that baseline, you can see why any claim of a sunward-pointing feature immediately triggers a scientific checklist. Is it dust? Is it ions? Is it geometry? Is it timing? Is it particle size? And only after all of that do astronomers start entertaining more exotic explanations. What got everyone's attention wasn't just that Three Eyes Atlas had a tail, it was how the light around it was shaped in some of the clearest post-perihelion images. Instead of a nice symmetric fuzzy ball with a tail streaming away in the expected direction, observers started reporting a coma that looked stretched into a soft teardrop with a faint extra extension that seemed to reach sunward. In other words, the bright head of the comet didn't just sit there and fade into darkness evenly. It looked like something was pulling the glow into one particular direction, like a candle flame leaning in a breeze, except the breeze, in this case, should have been pushing material away from the sun, not toward it. A big part of why this became a serious talking point is that it wasn't based on one shaky snapshot. The specific imagery that kicked off a lot of discussion came from post-perihelion observations in November 2025, and the reported sunward feature wasn't described as a tiny, ambiguous nub. It was described as an extension on the order of about an arc-minute toward the sun. That's a meaningful angular size in astronomy terms. Not blink and you miss it, but something you can measure, compare night to night, and argue over like adults. The method used matters too. Faint comet structures are often buried under noise, atmospheric turbulence, sensor grain, light pollution gradients, and the simple fact that you're trying to photograph a ghost. So observers frequently use image stacking, combining many shorter exposures to increase signal to noise and pull out delicate details in the coma and tail region. In the case highlighted in the discussion around Three Eye Atlas, one example cited was a stack of many 60-second exposures taken with a small telescope, producing an image where the teardrop coma and the sunward extension are easier to see than they'd be in any single frame. Stacking doesn't automatically make something real, but it does make it inspectable. If a feature survives different processing choices, different observers, and different nights, it starts to look less like an artifact and more like a genuine structure in the sky. Another reason the "what are we looking at" question escalated is that Three Eye Atlas wasn't showing just one dramatic thing. Images discussed publicly around this period show the comet with multiple components: a coma, signs of tail structure, and this debated anti-tail-like feature, very much the kind of multi-part comet scene you'd expect to see when a comet is active and geometry is changing fast. NASA's Apod even described a view of Three Eye Atlas showing a green coma, a blue-tinted ion tail, and a slight anti-tail, framing the overall scene as containing typical cometary attributes, which is a useful reminder that anti-tail as a word is not automatically new physics. And if you listen closely to how observers talk about this, you'll notice they're careful with direction words. They don't just say it points left, they talk about the sunward direction, the anti-solar direction, and the position angle of features. That's because comet images can be rotated, mirrored, cropped, and stretched. Left and right can lie. The reliable way is to anchor directions to the sky, celestial north/east on the image, and the computed sun-comet geometry at the time of exposure. Amateur and professional observing guides explicitly describe recording tail orientations by position angle, measured from north through east, precisely so you can compare structures across different images and observers, a SSA. So the visual claim, in plain language, is this. In some post-perihelion images, the bright coma of Three Eye Atlas isn't round. It's elongated, and that elongation is oriented in the sun's direction, rather than cleanly away from it. Some researchers have treated this as potentially more than the classic anti-tail illusion, and have debated whether it might represent a genuinely sunward-biased structure in the coma itself. Now, before you let your brain sprint into sci-fi territory, this is where the boring explanations enter like responsible adults with clipboards. Because comet tails are notorious for doing impossible things that turn out to be geometry. The most famous, most reliable, most annoyingly effective mundane explanation is the classic dust anti-tail. Not a tail that is physically blown toward the sun, but a thin sheet or trail of large dust grains that the comet left along its orbit, that suddenly becomes visible when we view it at just the right angle. NASA's APOD has explained this cleanly in past examples. When Earth approaches the orbital plane of a comet, dust that's been spread along the orbit can appear as a long, narrow anti-tail, because we see that dust sheet nearly edge on, making it look like a sharp spike. The dust is real. The wrong-way tail effect is largely perspective. Sky and Telescope has described the same basic idea in modern observing terms. Perspective changes can make tails look long and graceful when viewed broadside, or compress them into wedges and spikes when viewed more head-on. And anti-tails are strongly linked to the right-angle alignment between Earth and the comet's orbital dust. That perspective explanation also comes with an important detail that people often miss. Classic anti-tails are usually briefly prominent. If the anti-tail effect depends on Earth being near the comet's orbital plane, the wow alignment can be short-lived, sometimes on the order of days, because all it takes is Earth moving a little in its orbit for the edge-on stacking effect to weaken. That's why you'll sometimes see reports like, "It appeared suddenly," and "It faded quickly," even though no dramatic physical change happened at the comet. Another boring explanation is particle size. Dust is not one thing, it's a whole population. The small grains get pushed hard by sunlight and peel into the familiar dust tail. The big grains behave more stubbornly. They hang closer to the orbit and form trails. That's exactly why anti-tails are associated with larger, heavier particles that can stay organized along the orbital plane rather than being instantly swept into a broad fan. When you see a thin, anti-tail-like spike, you're often seeing the big grain component of the dust environment, made obvious by geometry. Then there's a geometry trick that's even sneakier: foreshortening. A tail can be perfectly ordinary and still look strange if we're viewing it at an awkward angle. If we're not looking at the tail broadside, we're seeing it partly down the barrel, and long structures can compress into shorter, brighter features near the comet's head. Sky and Telescope explicitly notes that head-on views compress and foreshorten tails into wedges and spikes. So something that looks like an oddly shaped inner coma can, sometimes, be a tail whose extended length is mostly pointed toward or away from our line of sight, hiding its true form. And now for the most unfair illusion of all: forward scattering. Comet dust is fantastic at scattering sunlight, and it doesn't scatter it evenly in all directions. Under some geometries, especially when the comet is positioned so sunlight comes from nearly behind it relative to us, dust can preferentially scatter light forward toward the observer. This can produce dramatic brightening and can emphasize certain dust features, making the inner coma and near-head region look more intense, more structured, and sometimes more directed than you'd intuitively expect. Sky and Telescope has discussed forward scattering in the context of comet brightness surges, and technical comet literature treats it as a real, measurable effect. Lowell Observatory also summarizes how dust scattering efficiency can rise strongly in the forward direction. So if you're trying to explain the visuals to a general audience without misleading them, you can frame it like this. Sometimes the anti-tail isn't a tail misbehaving, it's older dust arranged along the orbit that we're suddenly viewing from a special angle, plus lighting effects that make certain parts of that dust environment pop like a reflective fog bank in headlights. Now comes the crucial nuance, and this is where 3i Atlas gets interesting even for skeptics. Not everyone agrees the classic perspective anti-tail explanation neatly covers what was reported here. There is peer discussion level work arguing that the observed sunward feature in 3i Atlas may not be the usual orbital plane dust sheet seen edge-on scenario. One detailed proposal, on Argav, treats the anti-tail as a real sunward anisotropy in the distribution of grains near the coma, essentially a sunward extended region where sublimating ice grains can survive longer, a kind of directional snowline effect, due to how illumination angle affects sublimation and grain lifetimes. In that framing, what you're seeing is not simply a dust trail illusion, but a brightness structure shaped by the physics of sublimation and outflow in a direction-dependent way. And that tension between this is a classic anti-tail illusion and this might be a different kind of sunward structure is exactly why the observational details matter so much. The date, the heliocentric distance, the phase angle, the processing methods, the consistency across observers, the way the brightness profile falls off with distance from the nucleus. Those are the levers you use to decide whether you're looking at 1. An orbital dust sheet seen edge-on, 2. A foreshortened ordinary tail, 3. A lighting, scattering enhancement, or 4. Something genuinely unusual about the coma physics in this interstellar visitor. The swarm of object idea starts with something wonderfully unromantic. Comets don't fly like pure cannonballs. When sunlight heats an icy nucleus, gas and dust stream off the surface. That outflow acts like a weak, natural thruster, producing a non-gravitational acceleration on top of gravity. In the case of 3i Atlas, Avi Loeb points to tracking from JPL horizons, indicating a small extra acceleration whose dominant component is radially away from the Sun, at a level he summarizes as a fraction delta approximately 0.0002 of the Sun's gravitational pull. Now comes the key move. Suppose the comet isn't alone. Imagine a loose cloud of nearby companions, anything from meter-scale chunks to pebble piles to inactive rubble, travelling with essentially the same overall orbit, but not experiencing the same outgassing push as the main nucleus. If the nucleus is being gently shoved away from the Sun by its own mass loss, while the companions are not, then over time the nucleus will drift slightly farther outward than the companions. From our perspective, those companions would tend to sit sunward of the nucleus, creating a persistent-looking anti-tail geometry, even though nothing is actually being pushed toward the Sun. It's not that the tail is defying solar forces, it's that the reference point is sliding. The comet's nucleus becomes the moving target drifting away from the Sun relative to nearby pieces that are co-moving but less thrusty. Loeb's post goes even further and tries to show that the scale of this effect can land in the same ballpark as the observed morphology. Using his delta and a heliocentric distance, he gives us about 270 million kilometers. He estimates the relative displacement would be on the order of 54,000 kilometers, mapping to roughly 0.7 arc minutes on the sky. Comparable, he argues, to the reported sunward elongation of the GLOW extension in November images. That's the core, a geometric offset created by differential acceleration, not a literal sunward wind. Then there's the brightness puzzle, because in telescopic images, what we see is mostly scattered sunlight. A cloud of many small bodies can have a staggering amount of total surface area, even if its total mass is tiny compared to the nucleus. Loeb illustrates this with a toy example. If you had something like 10 to the power of 12 objects containing only approximately 0.1% of the nucleus's mass, their combined area could still dwarf the nucleus's area, meaning the swarm could dominate the reflected light and appear as a big, diffuse, coma-like glow. In that framing, the anti-tail isn't a single streamer. It's the bright side of a loose entourage, preferentially positioned sunward of the nucleus, because the nucleus is the thing being pushed outward. One subtle benefit of this hypothesis, purely as a storyteller's hook, is that it makes the anti-tail feel less like a weird hair flip and more like a formation flight problem. The comet is one dancer, the swarm is another, and the choreography is written by tiny differences in how strongly each piece responds to sunlight-driven activity. It also leans on an observable reality. 3i Atlas does show a strongly asymmetric, teardrop-like dust environment in high-quality imaging, so the question becomes not is something asymmetric happening, but what kind of asymmetry is it? But if you're going to present this responsibly, there's a crucial line to underline. A swarm sounds exotic, but it doesn't have to be. In comet science, a primary nucleus plus companions fragments is not science fiction. It's Tuesday, comet split. They shed pieces, they crack, they pop, they crumble, and sometimes they do it in spectacular chains. Researchers have long described nuclear splitting as a relatively common phenomenon, even if it's often hard to detect because companions can be faint, diffuse, and variable. And comet fragmentation doesn't just produce one extra lump. It can generate a whole spectrum of secondaries, from large fragments down to dust, with telltale signatures like outbursts, arc-like coma wings, and multiple condensations embedded in the coma. We've also watched it happen up close with powerful telescopes. ESA, for example, highlighted Hubble observations of comet 73P/Schwarzmann-Wachmann, 3 breaking apart into many pieces, an explicit reminder that a single comet can turn into a string or cloud of fragments on human observable timescales. And historically, Shoemaker-Levy 9 is the iconic case of a comet turned into a train of fragments by tidal forces, with the underlying physics of splitting and fragment motion studied in depth. So where would a swarm around 3i Atlas come from naturally? Start with stress. Comet nuclei are fragile, porous, and often described as rubble piles or weak aggregates. As they approach the Sun, thermal stresses can widen fractures and drive surface evolution. ESA's Rosetta team has discussed how repeated heating-cooling cycles can crack and reshape comet surfaces. Add to that the internal pressure of volatiles trying to escape, plus jets that act like localized blowtorches, and you get a body that's constantly being pried apart. Then add a second stress. The comet can effectively self-load stress on its sunward side. In one proposed disruption mechanism, sublimating gas can produce dynamic pressure and differential stresses that help fracture and fragment the nucleus, especially for comets that get strongly heated. Even when the details vary by comet, the theme is consistent. Sunlight doesn't just make tails, it can also help make debris. Now zoom into how this could resemble Loeb's geometry. A fresh fragment cloud near the nucleus is not a tidy single clump. Some pieces are active, outgassing. Others get quickly mantled in dust and become comparatively inert. Some tumble and vent, others don't. In that scenario, it's completely plausible for different pieces to experience different non-gravitational accelerations. Exactly the ingredient Loeb needs. fragmentation studies explicitly note that secondaries can have different lifetimes and show different non-gravitational behaviour, so you can paint a very ordinary picture that still looks dramatic in the sky. 3I Atlas rounds the sun, activity increases, jets intensify, a weak zone fails, the nucleus sheds a halo of chunks. The main nucleus remains vigorously active and gets pushed radially outward a hair more than the fragments. The fragments, being less active or inactive, lag slightly sunward in relative terms, and because there could be many fragments, their combined reflective area can outshine the nucleus in scattered light, producing a teardrop glow and a sunward-leaning extension, an anti-tail that's not one stream of dust, but a luminous crowd of tiny bodies and their dust skins. If you want an extra layer of plausibility for your narration, 3I Atlas is already known to be dusty and asymmetric in Hubble imaging, showing a teardrop-shaped cocoon of dust off its nucleus. That makes it easier to believe the system could also host structured outflow, and potentially debris very close to the nucleus, because it's not behaving like a perfectly symmetric, gentle emitter. And crucially, a swarm does not have to mean hundreds of kilometre-scale mini-comets. In comet breakups, you can end up with a distribution that is dominated by small pieces, from house-sized chunks down to gravel and dust. The smaller the pieces, the larger the total surface area per unit mass, so you don't need much mass to make a big reflective cross-section. That's why, from a purely physical standpoint, Loeb's brightness argument, surface area beating mass, is at least directionally sensible, even if the actual numbers would need careful observational constraints. Of course, science doesn't let you keep a hypothesis just because it's cinematic. The swarm idea competes with other explanations that are also grounded and in some cases more established, like models where the sunward anti-tail is tied to the behaviour and survival of ice grains in the coma under anisotropic illumination. There's even work explicitly modelling 3I Atlas's anti-tail as a sunward extended snowline effect for sublimating grains rather than a perspective artifact or a companion cloud. So the honest way to present the swarm possibility is, it's a testable interpretation that tries to connect two observations: 1. A sunward elongation, and 2. A reported non-gravitational acceleration by introducing a third ingredient, nearby bodies that don't share the same acceleration. Whether those bodies are real fragments, or the glow is instead dominated by ice grain physics, or we're seeing a more standard dust geometry illusion, the great part is that the universe doesn't care which story you prefer. It will answer with more data, changes in shape, motion, and brightness that either behave like fragments in formation or like dust and gas in a well-understood solar wind environment. If you really want to separate a normal comet doing normal geometry tricks from something genuinely different is going on, you end up treating the sky like a crime scene. You don't fall in love with one pretty image. You collect repeatable measurements that survive different telescopes, different filters, different processing, and different nights. The first thing astronomers do is lock down the geometry. Any claim that something is sunward has to be checked against the calculated Sun-Comet-Earth angles and the projected directions on the sky. The anti-solar vector, the comet's projected velocity vector, and the orientation of the orbital plane. The reason is simple. A dust feature that sits in or close to the comet's orbital plane can appear as a narrow anti-tail when we view it edge-on, even though every dust grain is still obeying radiation pressure and solar gravity. This isn't hand-waving. Comet dust tail analysis has a whole toolkit built around it, especially synchrone Sindine modelling, which predicts where dust released at different times and with different radiation pressure responses should show up in projection. That modelling step is more powerful than it sounds. A classic anti-tail illusion makes very specific predictions. It should line up closely with the orbital plane projection. It should be dominated by large low beta grains, particles less affected by radiation pressure, and it should often become prominent when Earth's viewing angle is favourable. Observational papers on anti-tail-like structures repeatedly note how strongly these features correlate with near-orbital plane viewing geometry. Then comes the time series, the part that makes pretty pictures behave like data. If the feature is a dust sheet projection effect, its apparent orientation and length should evolve in ways you can reproduce with geometry and simple dust dynamics as Earth and the comet move. If, instead, the feature is a cloud of companions, you'd expect a different kind of evolution. Not a smooth, model-friendly fan, but structure, knots, condensations, and a relative offset that persists even as viewing geometry changes. And if it's an ion/plasma feature, you'd expect it to track solar wind conditions and generally align with the anti-solar direction, rather than staying stubbornly sunward. That's why the next major test is multi-filter imaging, and ideally narrowband imaging. Dust mostly shows up in continuum filters because it reflects sunlight. Gas species show up in emission bands, CN, C2, etc. And the ion tail can be highlighted by filters sensitive to ionic emissions. If the sunward extension is a dust phenomenon, it should be strong in continuum and behave like dust in brightness profiles. If it's primarily gas or plasma, it should pop in gas bands and behave differently in shape and variability. This compared dust versus gas morphology approach is standard in coma studies, and is also why many comet observers use dedicated comet filter sets rather than plain RGB. O. UP academic. After that, you go from what does it look like to how does the light behave, specifically surface brightness profiles and polarimetry. Polarimetry is wildly underrated in popular coverage because it sounds technical, but the intuition is straightforward. Dust grains scatter sunlight in a way that produces polarization signatures that vary with grain size, composition, and structure. If your anti-tail is mostly dust, it will generally carry a dust-like polarimetric signature, and you can even look for changes with distance from the nucleus or between jets, coma, and tail regions. Researchers have used polarization spectra and spatial polarization maps to infer dust properties and to track how polarization changes across the coma and tail. Why does that matter for the swarm idea? Because a swarm of comparatively large solid bodies, or rubble, could, in principle, shift the scattering behavior away from the fine dust-dominated signal you'd expect in a normal coma. Even if every fragment is wrapped in dust, the mix of particle sizes and the way light scatters can change measurably. There are also techniques that use the point spread function in polarimetric images to detect weak coma activity or separate nucleus-like light from diffuse coma light, useful when you're hunting for compact companions embedded in a glow. Now for the most direct swarm versus no swarm test, high-resolution imaging and astrometry that explicitly searches for co-moving point sources, companions, near the nucleus, then tracks their relative motions across multiple epochs. This is exactly the kind of workspace telescopes excel at. Hubble studies of split comets have resolved clusters of fragments, measured their projected separation speeds, and used those motions to infer ejection times and fragmentation histories. In one HST study of a split comet, 332P/Ikea Murakami, fragments were seen receding from the parent at projected speeds ranging from fractions of a meter per second up to a few meters per second. Tiny speeds that still add up to large separations over weeks and months. A real swarm hypothesis for 3I Atlas becomes much more compelling if repeated high-resolution images reveal multiple condensations with coherent co-motion and a physically plausible dispersion pattern. And it's not just about spotting dots. You'd want to see whether those dots move like fragments should, forming an expanding cluster, often distributed along preferred directions linked to outgassing or break-up geometry and fading or evolving as smaller fragments shed dust and disintegrate. Fragment debris literature emphasizes how studying fragment distributions can reveal structure and fresh surfaces of comet nuclei, so a detection would immediately become a rich physics story rather than a gimmick. At the same time, you can test the mechanism that makes the swarm idea interesting in the first place: differential non-gravitational acceleration. Orbit solutions for comets often include non-gravitational parameters, commonly expressed as components like A1 and A2 in standard models, to account for outgassing forces. These are routinely measured for comets, and the literature discusses their prevalence and behavior, especially for long-period comets. If 3I Atlas has a measurable non-gravitational term, that becomes an input to predict how far an active nucleus might drift relative to less active companions. There's also a very grown-up version of this test. Compare independent orbit fits and physical models, and check whether the inferred non-gravitational acceleration is stable or changes with time in ways consistent with outgassing. Studies of non-gravitational acceleration in unusual objects emphasize that interpreting those accelerations physically can be subtle, and that extrapolating trajectories outside the observed arc can carry extra uncertainty when non-grav effects are significant. So that's the toolkit: geometry plus model fitting, time evolution, multi-filter morphology, polarimetry and brightness profiles, high-resolution fragment searches, and dynamical fits with non-gravitational terms. Each one alone can mislead you. Together, they start cornering the truth. Now, why is the sunward direction such a big deal that it makes astronomers and audiences both lean forward? Because the sun is not just a light bulb. It is the dominant dynamical engine shaping everything in a comet's environment, and it does so in ways that are surprisingly predictable. Dust grains are pushed by radiation pressure. Ionized gas is swept up by the solar wind and magnetic fields. As a result, the sky around an active comet has a kind of built-in compass. Structures generally organize relative to the sun in characteristic ways. That's why tail points away from the sun is a cliché. It's the visible footprint of these forces. When something looks sunward, it's not just visually odd. It's a flag that says either A, you're seeing a projection geometry effect, or B, you're seeing a structure whose formation story is different from the standard tail story. And that distinction matters because it changes what the object is telling you about its dust population and activity history. A classic anti-tail generally implies substantial emission of relatively large grains at earlier times, material that can stay organized near the orbital plane and later become visible under favorable geometry. That's like being handed a record of what the comet was doing days or weeks earlier. Anti-tails are, in a sense, memory structures. They preserve information about emission timing and grain size that a fluffy, always changing coma can wash out. For 3I Atlas specifically, the sunward discussion is even more charged because it's interstellar. With an interstellar object, we care deeply about the inbound-outbound trajectory, the precise orbit, and how non-gravitational forces might bias our reconstruction of where it came from and how it behaves. Non-gravitational acceleration is not just a tail detail. It can alter orbital fits and increase uncertainties when you try to backtrack motion beyond the observed time window. That's one reason the literature treats non-grav behavior as a serious dynamical issue rather than a visual curiosity. There's also something psychologically powerful here. The sun is the one anchor point everybody understands. You can tell a general audience, this points toward the sun, and they instantly grasp the tension because they've internalized the normal rule. That makes sunward a narrative accelerant, but it's also why it's dangerous. Lots of totally ordinary comet physics can masquerade as anti-physics if you ignore geometry, dust dynamics, and scattering. The responsible move is to treat sunward not as a conclusion, but as a starting gun for testing. Finally, the sunward direction is a big deal because it can help distinguish between competing physical pictures that are all plausible on paper. A dust plane anti-tail has one signature set. A true physical sunward anisotropy in grain survival or emission has another. A fragment swarm has another. The sunward axis is the reference line that gives these models their discriminating power. In the end, pointing toward the sun isn't just a spooky visual, it's the coordinate system in which comet physics becomes legible. The moment you say interstellar object, you basically light a flare that signals every corner of the internet. Come speculate here. And with 3i Atlas, the ingredients were perfect for a hype cyclone. Rare category. Only the third confirmed interstellar visitor. A visually counterintuitive feature, anti-tail that seems to point sunward. And a famous contrarian voice willing to frame the weirdness as potentially extraordinary. Reuters coverage back in July 2025 already set the stage. This thing is on a hyperbolic trajectory, moving extremely fast and is not a threat to Earth. So the story is pure curiosity, not danger. From there, the media pattern is almost predictable. Step 1. A striking image or visual description spreads. Teardrop coma, tail pointing toward the sun, jets, multiple tails. Step 2. The language hardens from might to is, because certainty gets clicks. Step 3. The story drifts from comet physics is tricky, and geometry can fool you, to is this alien tech, even if the original technical discussion never required that leap. You saw that arc play out very explicitly in mainstream reporting. Some outlets amplified Avi Loeb's swarm of objects framing, emphasizing the mystery and the possibility of something unusual. But the quieter, steadier countercurrent matters more. Multiple astronomers and NASA-affiliated communicators kept repeating the boring sentence that saves everyone a lot of embarrassment later. It looks and behaves like a comet. NASA released and discussed imagery and observations from multiple missions and platforms, reinforcing that this is an active comet with a coma and tail behavior consistent with cometary physics, even if it's an interstellar example. This is where it's helpful to separate three very different things that often get mashed together online. A hypothesis. Maybe a swarm of objects could explain the sunward feature. A measurement. Images showing a sunward elongation/anti-tail-like structure, plus orbit fits that may include non-gravitational effects. A narrative upgrade. Swarm. Artificial probes. Malign intent. Only the first two are in the realm of ordinary scientific debate. The third is where headlines start driving the science instead of the other way around. The Guardian described NASA publicly pushing back on claims that 3i Atlas might be alien-made, emphasizing its natural comet behavior and downplaying the more sensational interpretations. And importantly, you can be skeptical of the alien leap without being dismissive of the real mystery. The anti-tail debate is legitimate because comets can genuinely surprise us. And because an interstellar comet is a rare lab sample from another planetary system, even within the more technical literature there are competing explanations that stay entirely within known physics. For example, there's a detailed modelling approach arguing that what looks sunward could be explained as an anisotropic extension of an ice-grained survival zone, a kind of direction-dependent snowline, rather than a pure perspective illusion. So how do you talk about the media frenzy in a way that keeps your video compelling and responsible? A good strategy is to narrate the two speeds of the story. The internet moves at the speed of vibes. A single image becomes a conclusion. Science moves at the speed of repeatability. A feature becomes a question, then a set of tests, then eventually a constrained answer. And you can make that contrast feel dramatic without turning it into a conspiracy. Because the real drama is methodological. The universe is offering an ambiguous clue, and everyone's trying to figure out which explanation survives contact with more data. Which brings us to the satisfying part, the what happens next phase, where the sky itself starts voting. As of early December 2025, 3i Atlas is already past perihelion. Closest approach to the Sun was projected for late October, and it continues outward. That outbound leg is incredibly valuable because many weird comet features either A, collapse into something ordinary as the geometry changes, or B, reveal themselves as something physically distinct because they evolve in the wrong way for dust geometry explanations. NASA's Punch mission, for example, has been able to track the comet's tail evolution using combined and repeated observations over time. Exactly the kind of dataset that helps distinguish a transient projection effect from a persistent physical structure. Here are the concrete observational outcomes that can genuinely settle the dispute, and they make great narration beats because each one is a fork in the road. If it's a classic dust anti-tail illusion, you expect the sunward-looking feature to be strongly linked to viewing geometry. As Earth-Comet's sun angles shift, the apparent direction and prominence should change in a predictable way. The feature may appear sharp at certain times and then fade or rotate away without requiring any dramatic change in activity, just changing perspective. If it's a physical ice grain / snowline anisotropy, you expect a dependence on heliocentric distance and heating. The sunward extension should weaken or transform as the grain lifetimes and sublimation rates change. In fact, follow-on modelling work explicitly discusses an evolution where the sunward anti-tail diminishes and a more conventional anti-solar tail becomes more prominent as conditions change and grain populations shift. If it's a swarm of companions / fragments, now you're hunting for structure that behaves like objects, not dust. That means consistent knots or condensations, relative motions that can be tracked night to night, and perhaps a distribution that expands over time like a fragment cloud. You wouldn't necessarily see a clean, smooth tail. You might see a grainy morphology that resolves differently at higher resolution. Even some popular science coverage notes the tension here. Loeb has at times acknowledged images showing a single body without clear breakup evidence, which is exactly the kind of detail that pressures the swarm interpretation to make more specific, testable predictions. The big reason this next steps phase is so powerful is that none of it requires guesswork about motives or intent. It's purely, does the feature evolve like dust, like sublimating grains, or like fragments? And every week that passes provides another data point. There's also a very practical milestone that makes for a clean narrative timestamp. Multiple outlets reported 3i Atlas's closest approach to Earth, expected around December 19th, 2025, still at a safe distance. Even though closest approach doesn't mean close in human terms, it often corresponds to a period of strong public attention and heavy observing campaigns, more eyes, more instruments, more chances to cross-check morphologies and spectra, and the strongest science wins move you can make in your script is to explain what would count as a decisive result. A multi-epoch sequence showing the sunward feature rotating, fading, exactly as orbital plane geometry predicts, favors dust projection. Spectral or photometric evidence that the brightness is dominated by a particular grain type that should have a direction-dependent survival length, favors the ice grain anisotropy model. Direct detection of multiple compact co-moving sources near the nucleus at high resolution favors fragmentation/swarm. None of the above, plus erratic changes correlated with solar wind conditions, pushes attention toward plasma/space weather effects. Finally, there's a meta lesson that's worth making explicit to your audience, because it lands beautifully. Interstellar objects are so rare that our pattern recognition instincts are basically undertrained. With only a few examples, Oumuamua, Borisov, now Three-Eye Atlas, the temptation is to treat every oddity as a sign of the extraordinary. But the more disciplined approach is almost the opposite. Assume it's natural, then see if the data forces you to abandon that assumption. That's not closed-minded. That's how you avoid getting played by your own excitement. If you frame it that way, Chapter 9 becomes the story of how mythology forms around a blurry glow, how the word interstellar turns curiosity into certainty hunger, and Chapter 10 becomes the story of how the sky patiently corrects us with better evidence, night after night.